Hi everyone, welcome to the new video. We are starting now to go deeper into this idea of solving linear equations. We've seen linear equations set up, we sort of talked about how we can tackle the problems, but going forward we're going to talk about systematic ways or algorithms to solve linear equations. I see I'm missing a Q here. Now, let's start with an example. A typical example, something you've all seen in high school, maybe even elementary school, is a system of two equations and two unknowns, such as the one that we have here. Now, when we have a system of equations, we're trying to find these variables x and y so that the two equations are simultaneously true. Just by trial and error, you can see here that if you plug in a 3 for x and a 1 for y, you are going to get equality in both cases. Let's look at that just very quickly for the first equation. So for example, 3 minus 2 times 1 is indeed a 1. For the second equation, 3 times 3 plus 2 times 1 is really 11. So this point 3, 1, 3 for x and 1 for y, is a solution to the two equations. Now, what does this look like geometrically? You've probably all seen these pictures where you see that these equations, these are linear equations, and as I mentioned in the previous videos, that means that your variables, your unknowns, are only multiplied by numbers and added together. You don't have them multiplying each other or having them to some power. And so they represent lines. How convenient. Linear equations representing lines. So in 2D space, the first equation, highlighted in blue, corresponds to the blue line that we have on the right-hand side. And the second equation, highlighted in green, corresponds to the green line. The solution 3, 1 is the point of intersection of the two lines. This is what we refer to as the row picture. Now, there is another way to think about the two equations, and that corresponds to the column picture. So if I rewrite the system, I'll just quickly scroll in. So if you look at the top equations, you can describe that system of equations through vectors. So you see that in the first equation, x is multiplied by 1, whereas in the second equation, x is multiplied by 3. So we can describe that as a vector by saying that x multiplies the vector 1, 3. And then y multiplies the vector negative 2, 2. And when we add them together, we get the new vector 1, 11 that we have right over here. Right? So this is the exact same system, only now described through column vectors. What is new here in this picture is that now our x and y no longer represent a point where two lines meet, but rather they ask the following question: how much of the vector 1, 3 should I take, and how much of the vector negative 2, 2 should I take, so that when I combine them together, I get a new vector with coordinates or with components 1, 11. So what kind of linear combination of the vector 1, 3 and the vector negative 2, 2 do I need to take to produce this new vector b with the components 1, 3? And if you see now on the right-hand side where we actually have the picture, the vector 1, 3, oh, I guess I mixed these up. My bad. Blue and green really need to switch places here. Okay, let's fix that real quickly. So this is actually, it is correct, but it corresponds to, okay, I'll negative 2, 2 here. I don't want us having any mix-ups. All right, so you see in the picture, the blue vector really corresponds to negative 2, 2, and then the green vector is 1, 3, right there. All right, so now if you look on the picture, we see that, you know, if we multiply the vector 1, 3 by 3, that just means triple the vector, you get the vector 3, 9. And if you multiply, well, the vector negative 2, 2 is just multiplied by 1, which means what we've done is we've replaced 3 for x, and we have replaced 1 for y. So 3 times the green vector plus 1 times the blue vector gives us the purple vector, essentially. So you see the pictures are very different, and they reveal different aspects of the same story. Now, most of you will have seen this first picture. This is something that we typically see in calculus or pre-calculus. You have two lines, you plot them, you find the point of intersection. You can do that geometrically, you can do that algebraically, many different ways. Now, this new column picture is completely different, and some of you may feel like, well, you know, I already have a picture that I know how to think about. Why do I need this second one? Well, the nice thing is that even as you go to higher dimensions, this column picture stays the same. You're looking for ways to combine vectors to get some kind of vector, target vector B. Now, the matrix equation of the system consists of the columns that we have above right here, the columns 1, 3, and negative 2, 2. And that organizes the matrix A, the unknowns x and y, and then the vector B, which needs to be 1, 11. Now, the row picture that we have corresponds to obtaining the product A times X via the rows. So to dot products row of A dotted with the vector X. Okay, that I'm writing that X a little bit different, slightly different, so that it denotes sort of the vector X and not the component X. So this over here is your vector X. So when you multiply the matrix times the vector X using dot products, that gives you the row picture. If you carry out the multiplication via the columns, or rather looking at the matrix as a column combination of the columns, linear combination of the columns, so as follows: x times 1/3 plus y times negative 2, 2 equals 111. We saw that this is another way of carrying out matrix multiplication by a vector, and in fact our preferred way in this course because it reveals linear combinations. So this corresponds, the column picture corresponds to AX represented as a linear combination of the columns of A. And we will be coming back to this time and time again. Now, as I said, when we have higher dimensions, if we go to 3 equations and 3 unknowns, the row picture is given by the 3 equations where we have x, y, and z. Now, what do each of these equations represent? So in 3 space, each equation represents a plane. Now, we are looking, so it's analogous to the 2D system. we are looking for some kind of intersection of planes. Now, sometimes it could happen that planes don't intersect at all, and that happens when the two planes are parallel. If the planes are not parallel, then two planes will always intersect in a line. And then, so the intersection here of the two planes is a line. And then if we take the intersection of that line with the third plane, so intersection of a plane and a line is a point. Of course, it could happen that a plane and a line don't intersect, and that only can happen if the line is on a plane which is perpendicular to your original plane. But that's not the case here. So in fact, these three planes do intersect, and what we're looking for is a point of intersection. In the column picture, on the other hand, we are looking for the same thing. We're looking for a combination of the three columns, 1, 2, 6, 2, 5, negative 3, 3, 2, 1, to give us 6, 4, 2. Now, just pay attention a little bit in case you're confused as to how I'm getting these columns. The numbers 1, 2, 6 that multiply x, so that first column vector, these are just the coefficients of x in the three equations. So if you just focus on x, there is no number in front of x in the first equation, but that just means that x is being multiplied by 1. And so that's how you get that vector 1, 2, 6. Then the second vector really just records the coefficients of y in the three equations. And the third column vector 3, 2, 1 records the coefficients of z in the three equations above. And then finally the right hand side just gives us the vector b. By inspection of this system, it is actually very, very easy to find the point of intersection. Observe these two vectors. They are almost the same. Not exactly, almost. In what way are they almost the same? Well, in the way that b is 2 times the vector multiplying z. So if I call this vector v and this is the vector b, what we have is that b equals 2 times v. So what this says is that I can combine the three vectors in such a way to produce b. And what is that way? Well, I don't need the first vector. I don't need the second vector. And I'll take 2 of the third vector and I'm good to go. So actually we have this solution. 0 times 1, 2, 6 plus 0 times 2, 5, negative 3 plus 2 times 3, 2, 1 gives me 6, 4, 2. So the vector x corresponds to the vector 0, 0, 2. So we take that linear combination and we get our vector b, which is very easy. If you look at the row picture, it's not at all obvious. We have to do some kind of elimination, remove one variable at a time. It's going to take us quite a bit of work. We are going to try our best to use the power of observations, because sometimes it's really very obvious how the columns are combined, sometimes not so much. So we will use algorithms as well, but that will be in the next video. And finally, the matrix form. I just like in the second, in the 2 by 2 example. So these 3 columns are actually the columns of the matrix A. The unknowns x, y, z go into the vector x, and you have b as b. Again, the rows of the matrix A give the row picture, and the columns of the matrix A give the column picture. What is important for us is to see the product A times x or rather the vector B, as a linear combination of the columns of A. So this will be key for us. B is a linear combination of the columns of A, and X, the vector X, tells us, once we find it, tells us how to combine the columns of A to get B. All right, we'll see more in the next video.